Dear friends, welcome back to Technical, and today we are going to learn about something different. We are going to learn about regression analysis of spatial data types, and this is a very interesting topic that I've been meaning to start working on. And to begin us, let's create a folder, or in your working folder. In my case, I'm working on this code, so I'm going to create my folder here, and my notebook, not folder, but my notebook. And then this is what I'm going to use. So let me just name it regression analysis for spatial data. So this is the first time that I'm introducing the concept of spatial data, and there are some packages that you might not have in your laptop or in your machine that you will require in this session. So one of them is GeoPandas. GeoPandas is a package that allows you to handle spatial data types. These are data that have got coordinate or location information, and they are very, very unique from the normal data that you have. And this is why I thought it was a good way of starting to introduce it step by step. So if you don't have GeoPandas in your computer, I will recommend that you install it in a new environment or in a new Python environment. So first of all, you need to create a Python environment and then install GeoPandas. Don't worry, if you don't know how to do this, I'm going to demonstrate. So if you are working on a Windows, I will need you to open your command prompt. If you are working on a Linux machine, you will need to open the terminal. If you are working on OS or MacBook, you also need to open your terminal. So either way, Windows, command prompt, Mac OS or Linux, you need to open your terminal. So in my case, I'm working on MacBook, so I'll just demonstrate. So this is my terminal, and for you to create a new environment, you can create a new Python environment using Anaconda, and it's very straightforward. You just need to type conda, because you already installed Anaconda in your first lesson for this class, and then you give it a name. So the name will be, I will say something like geospatial, or just say geospatial. I'm not sure if I have geospatial library or Python environment in my computer, but so I've just added JA to make sure that I don't have any clash. So that is the name of the environment that I'm creating, and then in this environment I want us to install all the basic geospatial packages. In other words, these are Python, a set of Python libraries, functions, and methods that allows you to analyze or manipulate geospatial data types. That is the kind of data that has got location information, like the road data, the features on the Earth surface, maybe your GPS data or your Google Maps data. Any data that has got locational information, you will need this kind of packages. So, and take care, this is very, very important. If you want to install these packages, they are always very hard to install, because they lead to system upgrade or degrade. So the best way is usually to install all of them at once. So I'm just going to install one of the first one that we are going to use in this class is GeoPandas. And the next thing, you want to install all the related packages that GeoPandas needs to work with before all let it go. So I'll add pandas. Another common one will be Fiona. Another one will be Shapley. So you need to install them like this, exactly like this, so that it works for you. And R3 Descartes. I don't know if that's the right spelling, it's a French word. GDAL, and maybe just NumPy, just in case it's not bad, but it should be there. So once you do this, you just hit enter, and then you should wait, having Okay, so I missed something on my code. It should be conda. Before the name, I should add here create. So sorry about that. So it should be conda create to mean that I'm creating a new environment, and then just enter. And then it will try to start refreshing and creating the environment, and then it will ask me to proceed. So if you're on this stage, please just hit Y to mean yes, and it should proceed to install everything. It takes time, so don't worry. I've already installed it. I don't want to install it again. For the purpose of this for this video, I'll leave it at that point. So once you do that, the next thing now is, let's go back now to our data. I'm going to provide you with the data set for today. And the data set for today is in a geospatial format. And this is why I was explaining on how to install those packages. So you check the link. If you don't have, you check the link on this video, and you will see that data, or I will share the link where you can access the data that I'm using today. So a brief description of the data is very, very important so that you understand these basics before we can proceed any further with this class. So I'm going to share the data set that we have, and this is the data that we have. So it's an NDVI. NDVI, for those people who are conversant with geospatial data, is basically normalized. So NDVI, I'm just sharing what has been processed here. So for those who are conversant with geospatial data, NDVI is basically a normalized difference vegetation index, usually summed as NDVI. And it's a measure, in simple terms, it's a measure of how green a plant is. And usually it is an indicator on the health of a plant. So we assume that a plant, if a plant is green, then it's healthier than the one that is kind of brown or having some kind of different color. But that might not be the case for some plants because they're naturally green. So it's calculated by basically summing how much the plant reflects on the red and the near infrared, which is beyond the scope of this class. So the data, the most important thing is the data is provided in what is known as shapefile. So you might be wondering, what is a shapefile? So shapefile is a popular data model, or how we present data for our processing in a geographical information environment, or GIS environment. And unlike the case like you store your data in maybe Excel, shapefiles allows you to store data that has got location information. It shows the shape of that information. It can be a point, maybe just a dot on a map. It can be a line, something like a road or a river, or it can be a whole polygon, a shape, something like a boundary of a county, or maybe a boundary of a state, or something like a building. So that will be a polygon. So usually this data comes with other associated files. I will focus on some of the most important files. So the .shp file, this is the most important. It contains the geometry of the feature. So what is the which feature are you presenting? If it's a road, then it basically contains the coordinate that defines the length of that road. Or if it's a point, then basically it's going to be two sets of coordinate, the latitude and the longitude. And then if it's a polygon or something like a building, then it's going to contain a set of different coordinates that defines the shape of that building or boundary of that county or maybe a state. That is the .shp to mean shapefile. We also have .shx, and this contains the shape index, which allows for efficient processing of these geometries. So basically it contains the index, or kind of the key to the shape. And then we have got the .dbf. .dbf basically contains the data in tabular form. So if you look at your conventional Excel, we have got the rows and the columns. So this is the purpose of .dbf. So it defines how that data is stored in that shapefile. And then we have got the PRJ. PRJ, for those people who are conversant with geospatial data is basically the projection. So projection is the coordinate system. There are different coordinate systems used in a map. So this one defines the coordinate system that is used. And then we have got SBN and SBX. So these are just storing the spatial indices. So they look, it's kind of the key to the spatial component. And I think .xml is not important for this class. So when you are reading this kind of data set, you don't read all of this. You simply read .shp, and this one will basically retrieve that information from these associate files to have whatever you need. So that is the introduction to that data set. Important. Now, for our task today, we are going to also introduce the concept of regression analysis. And regression analysis is very, very important. It's one of the basic algorithms of machine learning that you can use to make predictions. So prediction is having making some inference or predicting something based on the data that you have already had. So for our class, we are going to use the common, we start with importing the common packages. So I'll use OS to navigate through my folders. I will use NumPy, of course, NumPy as NP. And then the most important one is GeoPandas. This is the first time we are using this package, and this is the package that is going to handle any kind of spatial data in our work today, GPD. And then I will use import matplotlib .pyplot as plt. And then I think today we'll use Seaborn, import Seaborn. If you have not installed Seaborn, please check my previous videos. I showed you how to do that. These are the packages that we are getting started with for now. So it's taking time to load. Good. The next is knowing where my dataset is. So I'm working on this folder called code, and you can see the name of my notebook is here, regression analysis for spatial data. So this is where my code is, but the data is stored in a folder, one folder behind in a data folder, and this inside this data there's folder called ndvi. So this is where my data is. So I need to navigate through that in a Python environment, and that is what I'm doing here. So I'm going to define the data path, in other words, the path where my data is located. So I know for sure I'm going to use .pypathJoin, the method in OS library. So I have to go one step behind to get to the folder that my data is in. But inside that folder is known as data. But inside that folder, we have got another folder that contains my data called ndvi. And you can see that clearly here, that we are here where my code is. And then I go one step behind and then get into the folder called data. And then inside that data, there's ndvi folder. And then the name of that file, as I said, we are going to only read this. Once we read that, it will automatically pick up the data that is required to read the whole. And then that is the path. The next thing is to read it as a geodata frame. So remember in pandas we read it at data frame, but here now we are using geodata frame to mean its data with the location. Geo basically means earth or location information. So we are using it geodata frame, which is a series of Python methods that allows us to read that kind of data sets. So I'm going to use GeoPandas, and then GeoPandas has got a method that allows you to read this kind of spatial data. And like in pandas that we use read CSV, if it's a CSV file or Excel, here we just use read file. And then once we do that, data path, I can I don't need to specify the name because it will not just pick the right one. So I can just say data path, but sometimes you might want to specify the name, but it's not necessary in most cases if you're just dealing with one shapefile in that folder. And then I'll just read the first few lines to make sure that my data set has read appropriately. Yes, so you can see this is my data set. It has got the name, which is the name of the station that was used to collect the data. And then we have got the NDVI that has been normalized. And then we have got these other variables. So the link, the definition of this, each of these is given on a research paper. So I'll share the link for those of you who are interested in the research paper that led to this. I will share the link here so you can look at it later on if you are interested in that kind of stuff. So that's the link. If you click on this link, it will show you the paper that was used to generate this data set, or the research paper that accompanied whatever we are doing today. Good. So this is the link for that paper. So each of these variables mean different things. Precipitation, PRCP means precipitation in millimeters. That is the amount of rainfall recorded in that area as it relates to NDVI. And then we have got the slope. The slope is basically the elevation in degree of that area, or sometimes the change in the elevation. And then we have got PERM, sorry. That is the permeability, which is how much this soil absorbs water in an hour, measured in inches per hour. And then thickness of the soil layer. And then we have got AWC, that is available water capacity of that data, of that area. And then the clay basically defines the amount of clay in that soil. So in some way, these variables that were measured contributes to the NDVI that is recorded by the instruments. And then we have got the geometry. The geometry basically is the spatial, or these are the spatial points, the coordinate that defines each of these stations. So you can see it's a point, which means it's just a dot on the map. So latitude and longitude. If it was a line, then you will see this to be line point, and then you will see several coordinates that defines the shape of that line. So I think that's enough. We don't want to get so deep because I just wanted to make you comfortable with working with spatial data as an introduction. Of course, ID and ID integers, these are just field station numbers. So these recording instruments have got some kind of unique identifiers that were recorded. So not very important. So whatever we are going to do now is to see if you read this paper, they are trying to show that the NDVI, or the health of a plant, has got a direct relationship with precipitation. Usually it is known that globally that if you look at a green plant, then the more green it is, probably, or if you have an area where there's a high amount of rainfall or precipitation, then plants in that area are likely to be green, which is very true. If you look at rainforest, tropical forest, very green and lush. But if the precipitation is low, take an example of deserts, of course with the exception of cactus, you will see that plants are not that green, they are different coloration. So there's a direct correlation between precipitation and NDVI. But this paper argues that that is not always the case. It varies from area to area depending on the location. And that is why they're including things like slope, they're including things like permeability, or how well that soil retains the water. They're including things like thickness, they're including things like available water capacity in that soil, and of course the clay content. So for this paper, all these factors somehow contribute to NDVI, and therefore we have to test how they do that. So I want us to introduce some concept known as multicollinearity, and I will just type it here. So this is a very important concept in data science, especially if you are working with the regression models. So what is multicollinearity? So I'll just define it. It is the occurrence, and I'll explain, of high intercorrelation among two or more independent variables in a multiple regression model. So what do we mean by this in simple terms? And I will use two different examples. So the first example, let's take a case of BMI, body mass index. So we know that body mass index is a measure of, I don't want to commit myself to definition, but body mass index, BMI, relates the weight of somebody with the height. So the formula for calculating BMI is usually the weight of the person in kilograms divided by the square of the height in meters. So in other words, if you are weighing 50 kg and you are 1.9 meters tall, your BMI will be 50 divided by 1.9 squared. So by just looking at that formula, that it's the weight divided by the height, it means that if I've got more weight, then my BMI is likely to be high. And if I'm taller, my BMI is likely to be low, because there's that indirect proportionality relationship between the height and the BMI, but there's a direct relationship between the BMI and the weight. So now sometimes you might find that the BMI is or you might find that these two independent variables, the height and the weight, are varying. They are related in such a way that, remember, if you are tall, it doesn't necessarily mean that you will have more weight. It doesn't mean necessarily like that. Or if you have more weight, it doesn't necessarily mean that you'll be short or you'll be tall. You can have more weight and you are still tall, or you can have more weight and you are very short. So sometimes these independent variables, so those are what we call independent variables, like the features that doesn't depend on each other, like weight and height. You might be tall, but you are having less weight. You might be short, but you have more weight. In other words, they don't depend on each other. So sometimes you might find in a cases whereby these independent variables like weight and height, they kind of relate to each other. In other words, if somebody is tall, then probability of them being having less weight is also high. So in that case, it might just be something out of chance or just the data that you are having, but it doesn't mean they're related. So in such cases, they might the effect of those two might lead to different BMI, and that is what we test or call multicollinearity. In other words, things that are not related to each other, they don't depend on each other, are showing some kind of a relationship. So it can be dangerous if you are building models, because the results on the eventual or the dependent variables is contributed by their interrelationship. In other words, if you take the two away, then their impact on the final dependent variable is not going to be high. So sometimes we need to test for this. And how do we test for that in this data set? So we test it using scatter plot. We can use to test for multi-linearity. So I want us to test it for precipitation. In other words, we want to see whether these independent variables, remember, precipitation, slope, these are independent. They don't depend on each other. You can have a high altitude area with high precipitation, or you can have a low altitude area with high precipitation, or something like slope with clay. You might find an area that is slope, but it has got high clay content, or a steep slope area with the low clay content. So I want us to test for different variables. So the first variable, let's just create a a general figure. So create a figure, plt.figure. Then we create the fig size. Usually I will go for 8. And that will be my figure size. And then the first thing I will do, I'll test for clay. So let me just write here, clay versus the NDVI. NDVI. So plt dot create the subplot. This is going to be my first plot, so it's gonna be 2, position 2, 3, 1 for the location. And then of course I'm making a subplot using Seaborn, sns.scalar plot. My x-axis, so usually what goes to the x-axis is the independent variable, the variable that doesn't depend on anything. So in this case, it's gonna be, let's start with clay. So this is going to be clay because the NDVI depends on clay. So it's going to be on the y-axis. And NDVI here in my data frame is given as VI. And then, of course, the data that I'm referring to is this data set, JDF. So I'll say data is equal to JDF. And then the next thing will be PLT. I can label the x-axis in a good way. So let's use clay. This is my x-axis. Label my y-axis. PLT.y label. This will be NDVI. And then the last thing will be the title, plt.title NDVI vs clay. Then here we go. So you can see there's kind of relationship between clay and NDVI. So let's look at what's happening here. You can see if the value of NDVI is 190, then the clay content value is almost 0, which tells us that there's a direct inverse proportionality. In other words, when one feature increases, the other one decreases. So the NDVI increases with the decrease in the clay content. And if you look at this data set, it kind of shows you that the general trend, such that when the clay content is very, very high, the NDVI value is very low. So I want us to do this for, let's do it now for precipitation. So that will be PRCP versus NDVI. So it's going to be the same thing. Let me just copy the whole of this. We don't need to plot that again, except we have to change this to 3, 2. It's going to be 3. In other words, we want 3 plots. So this means 2 plots, 2 rows, and then 3 columns. And then this is the second part. And here we are simply using said it's precipitation versus NDVI. So that will have to go. So PRCP, and then we can say label it as precipitation. Then label this like that, and then run it. So here we go. Now you can see there's a very clear relationship between NDVI and precipitation, in that the higher the precipitation, the higher the NDVI value. So I think we can just have this as millimeter to show that of course it's rainfall. Yeah. So there's a very direct relationship. As the precipitation value increases, the NDVI value increases, which is good. It goes according to what this paper says. The next thing will be permeability versus clay, or let's use NDVI first. So all the same thing, just copy the whole of this except the position, which is position 3 in the third column here. And then of course we are talking about permeability, so PERM, and then say here permeability, and the units for permeability is inches per hour. You can say here, change that to permeability, and see what kind of relationship exists. It's really hard to tell this kind of relationship because you can see they're scattered all over. So it's very hard to tell if there's any kind of relationship between these two. So I cannot comment on that. Maybe ecologists or agriculturalists can tell us more how these two relates to each other. The next thing that I want us to test is to test these independent variables, if there's any relationship between these independent variables, so that we know if there's any kind of relationship, then we need to select which one we work with. We cannot have the two of them, because if we have the two of them, then it's gonna water down our model. So the first that I want us to test is the relationship between permeability and clay versus clay. And I think there's going to be definitely some kind of relationship between these two. So here we're gonna have it on 3, and of course this is going to be 4, the fourth one. But here we're gonna have clay, then permeability, clay. Let's run it. Good. So you can see there's a clear, there's a relationship between the two. The permeability reduces with the amount of clay content. So in other words, the permeability is very low when the clay content is very high, and the clay content is very low in the case where there's high permeability. The next thing that I want us to test for is clay versus precipitation. So we just copy everything else. Here we use 5, and of course it's clay. PR. I guess that is how then clay. You can have this as clay, and precipitation. Yeah. So precipitation again is clay. The next thing that we're gonna do is test for the last one, which will be precipitation. Gonna be permeability versus precipitation. Just copy everything. It's going to be the 6th, and precipitation there, and then permeability here. Can have permeability on the x-axis, and then precipitation. And then run it. So this is what we have. Don't worry about this kind of mess on my graphics. Can solve that using PLT tight layout. And then of course do show them. Probably save these graphics. Fig. Save fig. And say multi collinearity dot png. Good. So we have this. We'll save it. Maybe if you wanna present it to your group or you wanna represent it in your report. The next thing that we're going to do is to test for the correlation between each of these variables. And as you learned from our previous class, it's very easy to test for correlation using inbuilt Seaborn functions. So let me just write here correlation. And here with just something so that you can remember later on. Check for correlation of variables by plotting. And you remember from our Seaborn classes, or when we started the introduction to data science, we say that we can test for correlation by doing a heat map. So we can plot a heat map. Remember, this is a markdown, sorry about that. So run it again. And it's very straightforward. We just select which variables we wanna test for. So for this case, I'm going to test for the NDVI, clay, permeability, and precipitation based on that paper. Feel free to test for other variables, but yeah, this is what I'm selecting. So let me just select, create a variable called variables, and then select the columns of data frame, which is I'm select the NDVI, and then I'm gonna select clay, and then select permeability, and then select precipitation. So those are the columns that I'm interested in. And then it's very easy to create a correlation. First of all, just we use the VARs. This is the columns that I've selected, or the data frame, the new data frame with the columns that I need. And then I just use the core function of Seaborn to do that for me. So once I've, so this one, it stores correlation. You can print and see what the values are. That is the correlation table, how each of these individual values relate to each other. So it's very straightforward. You can see there's a one-on-one correlation by NDVI, which doesn't make sense. You are basically asking how do these two things, which are identical, relate. And then there's a very negative correlation between clay and NDVI. In other words, if clay content increases, the NDVI reduces. There's a weak positive correlation between permeability and NDVI. In other words, NDVI slightly increases when permeability increases, but there's a very, very strong correlation between precipitation and NDVI. And of course, these are the values, you can interpret them. So let me plot this so that you can use it in your subsequent, if you want to use it in your report. So you can use PLT, define the figure size, then do fig size 8, 6. And then we're gonna have the heap map equal to SNS dot heap map. Then we annotate to have values labeled on the graphic. And then for color map, I'm gonna choose yellow. I'm gonna choose yellow, green, and blue. It's one of my favorite in Seaborn. And then of course have it plt.type layout, and then figs, save fig. I'm gonna call it correlation.png. I'm gonna save it as a PNG file and then show it display, and that will show. So this is just a representation of this table in a graphic format that you can present in your output when you're writing the report. Now, the next thing that I want us to do is to perform linear regression here. And this is where now I'm going to introduce the concept of linear regression as a model or as a method of machine learning. So, what is linear regression? So linear regression is a machine or a supervised method of machine learning that allows us to predict values given some attributes. So it's very, very important that we understand the concept of linear regression, because that entails everything that we are going to learn here. So let's take an example. And the way I explain linear regression, I usually use the real estate example. So let's say that we are looking at the prices. We want to predict the prices of houses in a town or in an urban center. So there are some factors that of course leads to the price of the houses, in that generally if you are close to the main business district, the prices of houses is likely to be high rather than somebody who is staying away from the business district. So such factors, it could be proximity to the CBD, that could be one factor. And another thing that will affect the price of the house will be the number of bedrooms the house has. So you expect that if a house has got 2 bedroom or a 4 bedroom, the prices should be higher compared to a house with a 2 bedroom. That is another factor that can contribute to the price of the house. The next factor that will contribute the price of the house will be closeness to amenities, or even things like coffee shops, schools, the security of the area. Those factors are likely to contribute to the price of the house, in that if a house is located in an area where there are no coffee shops, there's no grocery stores, there's no schools, there's no parks, the price of that house is likely to be lower compared to a house in a neighborhood with all those kind of facilities. Another thing will be availability maybe of broadband. If a house has got high-speed broadband or access to high-speed broadband, or it has got access to mains electricity, then the price is likely to be higher compared to a house that is located in an area where you have to find your way of connecting to the main grid or even accessing broadband. So those factors, we call them the features that define this. They affect the output, which is the price of the house. So if I give you a very good example would be, let me share an Excel file that I prepared for this. I think it will work in a good way to illustrate this. So this is a good example of the Excel file to explain the concept of linear regression. So our concern here is to estimate the price of the house based on these features. So in other words, the distance, which is the distance from the CBD, the number of bedrooms, the internet speed, proximity to school, or I would say proximity to amenities. So now each of these factors has got a direct implication on the final price of the house. So you can see this house cost 9 million Kenya shillings. The distance to the central business district is 43 kilometers. It has got 3 bedrooms. The internet speed is 25. Proximity to facilities is 2 kilometers. And then let's look at the most expensive house, which is 45 million. This house, the distance to the CBD is 7 kilometers. The bedrooms, it has got 4 bedrooms. The internet speed is 180. Proximity to amenities is 0.5 kilometers. So that contributes to the price of the house. So now, in machine learning lingo, each of these factors, we call them features. And then this is going to be the output. And for each house, so this could be, we can just have got a key here that identifies the house. So we can say this is house 21. This is house 34. This is house 56 or 45. I'm just coming with random figures. This is house 98. This is house 55. This is house 6B. This is house 7U. This is house 89D. This is house 56B. And this is house 78H. Let's have this as house 5G. This house is 78P. And this house is 32T. This house is 6Y. And this house is 9N. So these are just the keys to like the unique identifiers of these houses. So in this data set, each of these are attributes or features, and this is the dependent variable. In other words, the value depends on each of these attributes or features. So in machine learning lingo, these are features, and this is the dependent variable or the output. Now, each of these features can be considered as X, and each of these houses, we refer to them as data points. So, in other words, each of these individual houses is a data point. Now, the goal here is to create a function that when we feed with these features, it will help us to identify the price of a house. So in other words, now that you can tell you can feed all this data set to your computer, and I said at the beginning that linear regression is a supervised form of machine learning that allows us to predict values of a feature or predict some values. So right now we have got all these features and we have got the accompanying values. In other words, for each of these features, we know the price of the house. But there will be now a case whereby we have got all these features and our task is to predict the price of the house. So in other words, let's say that you are given a house like house number 9PK. And this house, you are told that the distance to the CBD is 31, and it has got 2 bedroom, and the internet speed for that house is 50 Mbps, and the proximity to other amenities is 3 kilometers. Now the task is what is the price of that house? Can you predict that house? So machine learning will help us to predict that price of the house, because we have exposed our computer or our model to several of such houses with different attributes and the same price. Now the task is our computer has to learn to generalize the general trend, or to fit a model that will allow us to predict the final price of the house. So the function learns, or the computer learns to do that by being exposed to several houses with given features as well as the prices. And this in machine learning is what we call training. So the machine model predicts the prices of the houses based on previous training. I guess that is clear. So that makes sense. So in essence, we are trying to predict the value or the price of the house for each data point, or for each of these, by multiplying the input variables, which are these features, by some set of coefficients. And these coefficients, we normally call them weights. So weights basically tells us the importance of a feature or an attribute. So if the price is 9 million, what is the most important feature that contributed to this 9 million? So if the most important feature is the number of bedrooms, then that feature will have got a huge coefficient. So we'll say that the weight will be big. It's normally from 0 to 1. So the weight will be huge compared to something like, let's say, the internet speeds, because that is something somebody can work out thanks to Starlink. Of course, Starlink hasn't sponsored this video. If you want them to sponsor, please reach them out. So now, each of these features has what we call weight, or how much important they are towards contributing to the final value. So if we have got a very small weight, then it means that feature is not important. So if you look at these features, probably the internet speed will not be very much important, but something like the number of bedrooms, because that defines the size of the building, will be extremely important. So that is the concept of weight. So now our aim is to build or to predict this value here, which we can say y, and I can just write the equation here. So each of these weights, we can call them theta, or for the purpose of this, let's say theta, we call them t to mean theta. And our goal is to multiply it with each of the variables. So the first variable will be, let's say, distance, which is d, or I'll just say d kilometer. So we multiply the weight, how important the distance factor is, and then we add it to the next one will be, again, theta, but this now it's theta 1 multiplied by the next important variable, which is bedroom, and then we add, let me write them at the top here, it makes more sense here. The next thing is to add the internet speed. So I'll have theta again 2, how much internet speed is important towards the price, multiplied by internet, and then plus proximity, so theta 3 multiplied by the proximity, which is p, and then this will help us determine the price, which is y, or the price of the house. So in other words, I googled something on the internet to help you illustrate much if you are not comfortable with Excel. So now this is the equation, the general equation. So each of these variables, theta 1, theta 2, theta 3, theta n, are the weights, or how much how important the feature is. And then x1, x2, x3, these are the features or the attributes. So consider x1 maybe to be distance, x2 to be bedroom, x3 to be the internet speed and up to xn, and then y is the value that we are predicting. So if you multiply the weights by the feature and then you add them together, they should be able to give you some form of prediction. And this is linear regression. I guess that can make more sense now. But how do we know if this model is accurate? So machine learning models like linear regression, you have to find some way of knowing if they are accurate or to test for their accuracy. So there are two ways to test for their accuracy. Either one is to test on how well they are performing. That is usually known as utility function. So how well is that machine learning model functioning? Utility. Other ways to test for it is to know how badly it is performing, and that is normally known as cost function. So if you're using the utility function, then you want to maximize it. If you are using the cost function, then you want to minimize it. Like you want to minimize how badly this model is performing. So for linear regression, the best way to evaluate how it is performing, you can use the utility function, which is normally known as the R squared, or you can use the root mean square, which basically is the cost function. It tells you how badly your model is performing. So again, root R squared will tell you is a utility function, so it will tell you how well your machine learning model is performing, and is normally runs from 0 to 1, or from 0 to 100%. 0 to 1 or 0 to 100%. So if your R square is close to 1, your model is performing really well. If you are using root mean square, then the values are usually from 0 to 1 and you want to minimize it. So if your value is very, very low, your root mean square is very low, then your machine model is performing well. But if it's close to 1, then you are really doing a bad job. So you need to make sure that you minimize the root mean square. So how I will focus more on the root mean square. And if you remember from your high school maths or high school physics, there's this concept of what we call best line of fit. So you do an experiment and then you fit in a line that best describes your results. So that was the first instance of your introduction to machine learning. So I got this image online, and let me share so that we can do that before we go to the so here is the values. So assuming that y is the price of the house and x is an independent variables, is a collection of independent variables. So the number of bedrooms, let's say for this case, let's just take one independent variable, number of bedrooms. So you will see that assuming that y is the price of the house and x is the number of bedrooms, then the prices of houses is increasing as the number of bedrooms increases, which makes sense. So these are the values that we have measured. These are the values that we have. Let's say that these are the houses that we know. And then once we plot them, we try to fit in a line that best describes each of them, such that if we extend this line to this point here, and we are given the number of bedrooms, we can read the corresponding value of y, and that corresponding value of y will be the price of the house. So essentially, if we fit this line, it should allow us to predict the value of the house given the number of bedroom, and this line is normally known as the line of best fit. So when you're fitting this line, whenever you're fitting the line on your data set or your observed data set, you want to minimize the distance between those observed data set and the line. So this line should be fitted in such a way that the distance between each of these values is very, very minimal. And that is what we call training of linear regression model. Again, that is how we train linear regression model. And the best way to check how well it is performing is to calculate the root mean square. So the root mean square will be each of the values on this line of best fit, this blue line here. Those are predicted values. They are not accurate values. But each of the values, each of these red dots, those are actual values. In other words, that is your data set. So what you want to do is to make sure that there's a very, very small difference between your predicted values, and the root mean squared is calculated using this simple formula, which is, so you realize that we are using mean square error instead of root mean square error, RMSE. Why are we using mean square error? The reason why we are squaring, first of all, these values is because if you subtract each of these values from the predicted values, then those ones that are above it will be positive and the ones that are below it will be negative. And remember, if you combine negative and positive numbers, at some point, you are likely to have got negative numbers. Or if you have got like 5, you have got 10 here and you have got negative 5, then negative 5 will reduce the value of 10. And once you reduce it, your model will be interpreted that, okay, I'm having a small root mean square error, which means my model is performing best. But that is not the case. That will just be because of the nature of the values. In other words, the negative numbers are driving the cost function down to mean that the model is performing best, but not actually. So to avoid that error, you square each of these, because any value that reduces a number, it also reduces its square root. So if you square these values, then you are going to reduce that influence of negative numbers. And that is why instead of using root mean square error, we use mean squared error, which is basically a square. We square each of these negative values to have positive values and then subtract them. So if you look at this formula, the mean square error is given by y1 minus y hat, and all of them are squared, and is a summation. So y1 is basically observed values. So those are the values that you get from your data set, like the number of the distance, and then the predicted distance, which is the predicted value, which is the price. And then you do a summation from I to n. In other words, from data point 1 to the last data point. And that will give you the mean square error. Now that you know that, let's implement a linear regression model in our data set. So to do that, Python has got a very good package. The most standard one, or even when we start learning a lot of machine learning, we'll be using scikit-learn package. But in this case, I want us to use a very simple one known as stats model. And the way we do it, you need to install it in your computer. If you don't have it, I guess you don't have it. So to do it, best will be go to your terminal again and do conda install on your terminal or on your command prompt, conda install -c, and then do conda forge stats model. Once you do this, it's gonna install it. So please do that. I've already done that. I will not do it on my part. But if, just to show you what's happening, is you need to open your command prompt. So this one should be no. And then you just copy that. And then once you do that, hit enter, and then it will install the stats model. So stats models allows us to do linear regression in Python environment. So it implements what is known as ordinary least squares, or OLS method. And least squares is basically trying to minimize that root mean square error that we were looking at the top. So the first thing that we need to do is to define, to use the OLS, we need to import it here. Once you install it, please import it here as, it's very straightforward to import it. You do import stats model s.api as sm, and then run it to make sure that you imported it correctly. Good. Mine works, so yours should work too if you follow that instruction. Now, let's see, apply a linear regression model. So the first step to apply it, we need to define the variables x and y. In the example below, we read the variables from the GDF file. So our variables are from this GDF file. So you can see these are our y in the case, because these are what depends on this other one. So the y variable is an dependent variable. In other words, it depends on other independent variables. Something like your BMI will be a y, or it will be a dependent variable that depends on your height and it depends on your weight. So we define that. So usually the dependent variable is on the y-axis, independent variable on the x-axis. So our y-axis will be the NDVI. So GDF, I will select just NDVI, which is VI. And then let's use, so the first one we're gonna do is to fit a linear regression model for clay versus the NDVI. So what we are trying to do here is, if you are given the clay content of a soil, are you able to predict the NDVI of a plant growing in that soil? And this is not only limited to soil. You can use this linear regression model for related work. For example, if I've given you, we know that the BMI of somebody is related to the weight and the height. So if I've given you a set of BMI and I've given you a set of weights, now if I give you a new weight, are you able to tell us the BMI of the person? So that is what essentially we're trying to do. So it's a prediction problem. So let me just clarify here. So this is NDVI against clay. Good. So let me make this bigger, smaller. So our dependent variables is the NDVI, which is denoted by VI in the column name, and then X. This is our dependent variable, and our dependent variable is clay. And then the next thing we do is to add some constant B naught to the equation using the stats model function, or first start model method called add constant. So X, and I will explain what that means. I will explain what that means. So let me explain what, let me just pull my figure here again. So what this constant means is basically the y-intercept. So if you remember your basic maths in high school or your physics in high school, if you draw the line of best fit, at some point it will cross the y-axis, or in other cases it doesn't cross the y-axis, it will cross it at 0. So the point at which it crosses the y-axis, the value of y-axis at that point is normally known as the y-intercept, or the constant. So if you remember the equation of a line, y is equal to mx plus c. That c indicates where that line is crossing the y-axis. And in reality, what that means is, for example, if you are looking at the price of the house and against the number of bedrooms, and let's say that it crosses the y-axis at 0.5 million, it means that 0.5 million is the price of the house when we don't have got any information, or we don't have got a bedroom value for that house. So in other words, it's a bias term. It's something that exists when the other one doesn't exist. So that is like the inherent value of the house even without a bedroom, because it doesn't mean that the house should have a bedroom. Some houses do not have bedrooms, just like a single room. So that makes sense. So it's normally called the bias term. So that is what we are adding here, because it's going to affect our model. So we do that by using the add constant method from the start model. The next thing is we use the OLS function, or the ordinary least squares method function, to perform the regression. So we do that using the OLS. So we can define our model using the SM that we imported, and then say OLS in capital, then Y, which is our dependent variable, and X, which is our independent variable representing clay. And then the next thing, it returns the results. So we can do results is equal to model dot fit. So we're going to fit that line of best fit, and then I want us to plot it. So plt dot scar, then gdf, and I want us to label. So we are just picking two values, clay, which is going to be on our clay is going to be on our x-axis, which is independent variable, it doesn't depend on anything, gdf, and then we have got the ndvi, which depends on the clay content of the soil, and then we label this. These are our data set. So these are the actual readings from that were collected by the instrument. So whatever this is plotting is these values recorded here. So it's plotting the values of V or the NDVI against the soil. And then now we are going to see the results of the predicted values that we have predicted using this stats model, linear regression model. So we can do plt dot plot, and then gdf clay, and then the results that we found using the line of best fit, and then use the method called fitted values to plot them. And then I want the colors to be let's have the color of that line to be red, and then the label, this is the results of the model. In other words, these are predicted results. Again, this is not limited to just this kind of work. You can do it for any kind of problem that shows some kind of linear relationship. Remember, the problem has to show some kind of linear relationship. You can't just use it anywhere else. And then we label X label clay, plt y label ndvi, and then let's plot the legend that defines which one is the data set and which one is the predicted values. So legend, and then the last thing is to plt that show. I will also add this tile layout and the correlation. So plt dot, and then I'll say linear regression. Good. So let's run it and see what we have. So we have clay, it's returning some error. Let me see what's the error. plt.scatter, plt, oh, double T, triple T, it's a problem. 7 fitted values, so results. Let me see what the problem is. Okay, so I forgot filtgdf.clay results. Red, pink color. Good. So here is our linear regression model, and this tells us it fits the line of best fit for clay and the NDVI. Of course, you can print out the performance metrics, the R squared of this, so that you know what values, or you can do a summary. So stats mode allows us to print the values, which gives us the extensive description about the regression results, so the evaluation metrics for this. So to do that, we can just print results dot summary, then print it, and this is a huge file of statistics that you can copy in your research work. So let's explain what some of the most important things are here. So the first one that I want us to look at is the R squared. So the R squared is 0.329, which means the model is performing really, really bad, because we say the R squared should be close to 1, but this one is 0.329. So the R squared is basically the coefficient of determination, and it's the proportion of the variance in the dependent variables that is predicted, or that we explain here. So it is how these variables, NDVI values with the predicted values. So the 3.29 is very, very bad, so we need to get something good. So probably clay is not the best, or we have to include other independent variables in this model. And then the ADJ R squared basically means the R squared adjusted, and this is the modified version of the R squared for the number of independent variables. So for these other independent variables like permeability, precipitation in the model. So the value of R squared increases when we include extra values, which is actually improving our model. So we can increase other values, such as maybe permeability, to try to make this line of best fit more better. And then we have got the F statistic, which is 18.6. This is the ratio of the mean square error of the model to the mean square error of the residuals, which are the prediction. It basically determines the overall significance of the model, so it stands at 18.62. The other important one would be, of course, there are the usual descriptive statistics like the skew, the kurtosis, which are like the first and the second moments of statistics. Not that very useful in this case. The coefficient values, these are the independent variables of the constant term in the equation. So the constant term will be where this line crosses the what do we call it? It crosses the y-intercept. And then we also have got the t. The t, I don't want us to introduce this at the moment, but just know that it's a statistic, and it's a ratio of difference between the estimated values, or the predicted values, and the hypothesis or hypothesized value of the parameter to the standard error. So that is a simple linear regression model applied to our data set. You can, for your case, maybe you can try to fit, because I can see the time is almost up. We are almost at the 1.5 hour mark. We can try to do the same for NDVI against permeability and see the results. So please, let's try to do that quick first before we go to the last part, or we finish up the video. I don't want the video to be extra long, because if we go extra long, then we start losing concentration. So let me use, so now we are doing NDVI against permeability. so that you understand, and then I challenge you to do the rest for other variables, not just this one. You can go beyond other variables. So let's first of all define our dependent variable, which is vi, and then we can do x gdf. I want us to see how the r square pans out here, and then add some constant, which is the bias term in our this is a bias term in our equation or in our line in our data set, and then we fit in the model. So use stats model.ols yx, then results, then we can do the scatter plot, plt gdf, then permeability, then gdf, the independent, which is vi, then I will label that is the original data set, and then do plt dot plot gdf, then permeability, results dot fitted values, color, let me use green this time, then label, let me label the model. I can say predicted to mean predicted, but generally just the model. Then let's do plt dot plot label will be permeability, it is inches power, then plt dot y label ndvi, then we can do the usual one, just copy the whole of this, then run our model. This is x label, made a mistake over there, sorry. Yeah, there we go. So this is our model, and then let's print out the statistics and see how our r square improves. So this will tell us which variables are very, very important in making this model to predict accurately. So our r square is even worse, 0.061. So we need to try and in the next step we can include more dependent variables and see how each of them contributes significantly to the output. So I want you to try this, or sometimes if you see that each of these independent variables, if you try to use them to predict the outcome, in this case the NDVI, so if you just use clay alone, we are getting an R square of 3.2, which is 32%, very bad. If we just try to use permeability alone to predict the outcome of the NDVI, then it even performs worse, which is 0.61. And this is where the concept of weights come in. So it means the level at which the importance of clay in predicting the clay content in predicting NDVI, clay content plays a very important role compared to permeability based on those two R squared values. So the best thing will be to try and combine these several independent variables in what is known as multiple regression. And to do that, let me just say here 3 multiple regression. Good. So remember now, like we are getting into the realms of machine learning, and you realize that there's no standard way. It's like cooking. If something is not working, you try to tweak or you try to fine tune it to get better results. And that is why some people say machine learning is not science. I don't know. I don't want to get into that discussion. But now let's try to include several independent variables and see if our model is going to improve. Our linear regression model is improving. Because we have noticed that if we are just including clay to predict NDVI, results is the mean square is 0.32. If we just include permeability, it's even performing worse. The result is 6%, which is terrible. Let's try to include some variables, and these variables that I'm going to select, I'm not selecting them magically. I'm selecting them based on the paper that I told you, this paper here, and I gave you the link. So these people has done a great research and realized, like, if you select these variables, which is clay, precipitation, and permeability, it really improves your model. So I'm not making this stuff up. I'm just following the researchers, and you will see magic that is going to happen to our model. So to do that, first of all, let's select our model GDF, which is our linear regression model, and then X. So now X here, we are not just selecting one independent variable, we are selecting the 3 based on that research paper. So clay content, that is the first one. The second one is precipitation, and the last one is permeability. So all this, we are going to have them in our model and see how the performance improves. And then we add some constant X. So this is the bias term. And then fit in the model, straightforward sm.ols yx, and then the results, which is the model that fit, and then we print the results, the summary of our results, and see if it improves. Let's run it. Hooray! See what we are having now. We are having an R squared of 80%, which means each of these 3 values, if we combine them together to make a machine learning linear regression model, then it improves significantly the performance of our model. So in other words, we can make more accurate prediction at 80%, which is very good. So this is just to tell you that if you have got several independent variables, they might be acting independently to predict the results, but if you combine all of them, it can massively improve your results. But then again, sometimes you don't want to combine most or all of them, because it will result to something known as overfitting, which means that it will learn very well on that data that you are using. But if you try to apply that to a linear regression model to a new data set, it might perform horribly. So you want to avoid that. you want to be very conservative with these values, just enough to make sure that your model improves well. So that marks the end of this tutorial. Today we have learned about reading geospatial datasets and handling them. We have also learned about collinearity, multicollinearity of datasets, and then the last part we have learned or introduced our first machine learning model called linear regression. If you love the video, please give us a thumbs up. If you have a question, please post it on the comment. I will be glad to answer. If you have any queries, please make sure that you reach out to the link. I will respond to that. I've attached the link to the dataset and this code so that you can access it. Please do so. If you have got any question, reach out. For now, bye bye.